Yeah, this is a especially weird year, so I don't know what we're going to do yet, but at some point I may have to meet with Sophia, figure out what we're going to do. We have a few teachers that we're looking into, so you, Seamuth, Joanne, Alice Nicole.
Are you guys, do you know if you guys are going live?
You know as much, if not more, than I do.
Okay.
I didn't even know. I didn't even hear anything about we stopped for coronavirus except for my students.
What?
That's the last thing I've had communicated to me about the academy was my students telling me we're not doing class next week due to coronavirus, and it never picked up again after that.
Oh my word.
So that is all the communication I have received.
No one even told you it was your students that told you?
Yeah, it was my students. It was either you guys or you guys.
Oh my word.
Yeah, that calculus class.
Yeah, so. Yeah, I'm not informed at all. Okay, so chapter 4. Chapter 4 is very similar to chapter 2. If you remember chapter 2, we were looking at, so you had your sentences. We were already comfortable with sentential connectives. And then we started looking at interpretations of sentences and then a sufficient condition for tautologies based off of sentential interpretations, right? So we had our crude check for a tautology was if every sentential interpretation is true, then it's a tautology. Now, it's kind of like what we want is a definition for a rectangle, and so far what we've been using is if it's a square, then it's a rectangle.
Right.
So we've been using if every sentential interpretation is true, then it's a tautology, which is true, just like every square is a rectangle. But what we really want is we want to work with rectangles. We don't want to limit ourselves to just squares. Does that make sense?
Yeah.
So we're going to come up with, in this chapter, chapter 4, we're going to come up with an interpretation that doesn't just preserve the structure of sentential connectives, but it's going to preserve the structure of the terms, the predicates, the sentential connectives, the quantifiers, and we're going to figure out how to handle interpretations with that and start looking at what those logically imply. So that's a big part of what chapter 4 is all about, how to do this using our 3 things that we added on, our quantifiers, our predicates, and our terms. So that's a lot of what we're going to do. The way that's organized is first, he introduces to us on how to bring inference with universal quantifiers into the picture. And then he's going to have the discussion about interpretations. And then we're going to come back and talk about how to deal with existential quantifiers, and then we'll go from there. You remember
we went over inference, right?
Huh?
Where we went over inference.
We went over inference with sentential interpretation. Right? So yeah, now we're going to go over it with universal quantifiers. Then we're going to go back and have a discussion about what interpretation is. Then we're going to come back and talk about it with existential quantifiers. And then how to use them together, and then some generalizations. And that will be the end of chapter 4. Chapter 4 is probably the most, what's the word I'm looking for?
Proof heavy.
When there's a lot of terminology, a lot of jargon. It's going to be a lot of jargon. Yeah, there's going to be a lot of technicalities, a lot of things that's easy to miss reading through it. So probably one of the most important chapters for you to actually read, go through, make sure you understand everything, because it's really easy to miss stuff. First time I read through it, I missed a lot of stuff. I had to read through it twice to pick up everything. At least I think I did. Who knows? Could have easily missed stuff still. That's what you guys are here for. All right. So let's jump into doing the proofs, basically derivations, where we only have universal quantifiers. That's where we're going to start. Okay? You remember what universal quantifier is? It's a for all.
For all. There exists.
Yeah. No, there exists is the existential. Means that at least one exists. Universal means it's universal. It's true for everything in the set. Okay. So the author outlines a basic strategy for how to do proofs that just have universal quantifiers. Symbolize the premises and logical notation. That's basically what we were getting comfortable with in chapter 3. Chapter 3, we were taking
Right.
formula, we were taking sentences in English and symbolizing them with our notation. So that's the first thing to do. Next thing you do, drop the quantifiers, drop the universal quantifiers, apply sentential methods of derivation. This is what we were doing before when we were doing proofs, and then put the quantifiers back in.
Drop the quantifiers.
Yeah.
Apply sentential.
So we'll do a nice easy proof with it real quick to see all this in action, and then we'll go over the basic strategy again and see how we're using it. Okay?
Potential methods were like when we did proof by contradiction.
Yeah, that was one of the things we did.
Right.
All the methods we developed.
Right.
Basically, all our tautological implications that we already have. Okay, so let's start with this example, and basically we're doing step 1, we need to
For all x.
symbolize it. All animals are immortal. What's this saying?
For all
animals,
x.
that animal is more.
For all x,
A of x.
A of x implies
is M of x.
M of x. Perfect. And this is just a premise. 2, all human beings are animals. This one's almost identical, right?
For all.
Yeah.
Now,
For all y.
we can use y, we can continue to use x, doesn't really matter.
Wouldn't you end up saying x equals y?
You're saying if I did a y here?
Yeah.
No. So let's make sense of why it doesn't matter if I do a y here. All human beings are animals.
Oh.
So if human applies to y, then animal applies to y, right?
Yeah.
So what is this saying? This is saying for everything in the universe that we're talking about, if it's a human being, then it's an animal. This is saying for everything in the universe we're talking about,
Right.
if it's an animal, then it's mortal.
Right.
It says the exact same thing if I use an x or a y here.
That only applies to, I'm guessing the universal quantifier wouldn't apply to the existential.
Yeah, this is just with universal quantifiers.
Yeah.
Yeah. Okay. Therefore, all human beings are mortal. That's what we're trying to get to, right? So we did the first part. This is what we're trying to prove, so we won't write that in there. We did the first part. We symbolized the premises in logical notation, right?
Drop the quantifiers.
The next one says drop the quantifiers. So this one might seem kind of weird, but here's the way we interpret it. So then I can say AX implies MX. Let me try and scroll just enough to. Oh, he's just saying drop the universal quantifier, but
Just so
we'll come back and give it that a special name. So right now we're just dropping it and we'll leave that blank for now. Now, the way that we think about this is we're saying if it's true for all x, then this universal quantifier just represents an arbitrary x.
Okay. Like equation?
So for example, in discrete math, if I was said something like, prove all integers divisible by 4 are even, right? So how would you start that? You start that, you'd have some set of things that you're talking about, everything divisible by 4, and then you'd say that, I don't know what we want to use. To use the set of everything divisible by 4, you start by saying let x in Q. You grab an arbitrary element of it.
Right, you do that kind of.
So if this is true for everything, then it's true for an arbitrary element in our universe.
Oh, so then you're saying x is a specific element.
It's not a particular
particular
element,
one,
it's not a constant.
Right, right.
But if it's true for any, it's true for an
Right,
arbitrary.
it becomes separate from any given. That makes sense. It's like it's a particular one.
It's a subset.
It's now we can start talking about this x.
Yeah.
Yeah. And then similarly, we know from this that if h applies to x, then a applies to x. Now there's no problem with going from y's to x's. We all understand why.
Yeah.
This was true for anything in the domain. including x.
Okay.
Good?
It's the same domain maybe.
Right. If this was true for everything, it's true for x. This is just saying it's true for everything. Y is kind of acting like a dummy variable there, right? Okay. And then we use, I haven't really been saying the premises that these depend on. Obviously, it just depends on 1, just depends on 2, just depends on 1, just depends on 2. And then now we can use what's called hypothetical syllogism, which is if A implies B, oh, what am I doing? All animals are mortal. Oh, I did backwards.
A implies.
If A implies B and B implies C, then A implies C. So, this HX implies MX is tautologically implied by 3 and 4, right? You good with that?
Yeah.
And then, so we did this, we applied the sentential methods of derivation, and then we put the quantifier back in. If this is true for an arbitrary element of x, this is true for every element of x. So then for all x, h applying to x implies m applies to x.
Yeah, we did that.
Simply tautologically implied by that.
Wait,
We're going to
so
come up
you-
with the names of these rules. They're going to be talked about over here.
So it's kind of just generalizing what we did in discrete math. It's the same idea.
What we did in discrete math is a generalization of this. Or, no, you said that right. This is a generalization of what we did in discrete math. Discrete math was a particular use case of this, because you use the same thinking in all of it. That's right. Okay? So let's make sure that this makes sense one more time. If it's universally true for every element that these two implications are the case, then both those implications are true for an arbitrary element. If they're true for any elements, they're true for an arbitrary element. Make sense?
Yeah.
And then, so this is true for an arbitrary element. If this is true for an arbitrary element, it's true for every element. Are you guys okay with me using the word element?
Arbitrary.
Element, member.
Arbitrary is where I get more confused.
Arbitrary, it's almost random. It's no particular, we were never talking about a particular element. We were never talking about a specific x. We were talking about an arbitrary x.
Just one of them out of the set. Any one.
You did this all the time in calculus. So, for example, you would use the Archimedean property to say that there exists some natural number n greater than whatever,
Right.
right? That's an arbitrary element n that just satisfies some condition.
Right.
This is just an arbitrary element x that happens to be in our domain. It's not a particular one, it's just some arbitrary one.
Okay.
Make sense?
That does.
The word arbitrary there? Okay. So, make sure we didn't miss anything he said. Oh, we did the same. Okay.
The intuitive idea.
Huh?
Just the way he said it was pretty good as well.
Oh, where are you reading
The
that?
intuitive idea of the rule is that whatever is true for every object is true for any given object.
Oh, that's another way to say it. An arbitrary element is any given element. Yeah, same thing. So, if it's true for every object in the set, it's true for any given element in the set. Good?
Right.
And if this is confusing, using the x's and the y's like that, we could have come down here and said z, 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 and it's still perfect without. Where z was just an arbitrary element in all these, and now we're saying it for every z. We're still just saying for everything in the set.
Right.
Anything confusing about that? Anything weird? Let's make it make sense now. All right. Let's continue then.
I would actually really
Huh?
No, that's when multiplication for that one.
No, it's close. Probably getting glare on there, huh? Oops. Okay. Okay, so the rule of, I just wrote US there, but it's universal specification, right? Yeah, universal specification. And this is basically the rule that allows us to go from here to here. So let's read exactly what it says. So, if a formula S results from a formula R by substituting a term X for every free occurrence of a variable Y in R, then S is derivable from, for all Y, R. So let's go back to this one. Let's say that here's my for all Y, and here's my R. Then here's my S, okay? So let's go over it again. If a formula S, that's this one, results from a formula R, that's this one, not with the existential, or not with the
You're
universal.
looking 1 and 3, not.
2 and 3. Oh, am I mixing them up? Okay, you're right. So let's get rid of those for a second. So here's my S, here's my R. Right?
Right.
Yeah. Okay. So a formula S results from a formula R by substituting a term Z, in our case instead of X,
Right.
a term Z for every free occurrence of a variable Y in R. Notice R does not include this piece. Here's R. It's just this formula.
Why?
Because we're going to go from this to S. We're using for all X, R, just like this uses for all Y, R. Okay? So R is just this formula. Maybe I'll write to the side.
But then R and S are identical.
R is just AX implies MX, and S is AZ implies MZ.
Those are literally.
You're right, it happens to be in this case that they're practically identical, but look at what the rule enables us to do. The rule is enabling us to go from this whole thing to this whole thing. So let's go through it one more time. So if a formula S results from a formula R by substituting a term Z for every free occurrence of a variable, notice in this formula, X is free. So we need to substitute every free occurrence of X with our new term, we chose Z.
Right.
You with me so far? Every free occurrence of a variable, we used X in R. Then S, this thing, is derivable from for all Y R. So we're saying,
For all X are in our case.
oh yeah, for all X R, thank you. So take this thing, replace all its free occurrence variables with some arbitrary term in your set Z. Then this is derivable from this.
Right. That makes perfect sense.
And it's the exact rule that we just barely were making intuitive sense of. If this is true for every object, then it's true for an arbitrary object, or for any object. It's still that same rule, just written down explicitly. Is there any confusion about this rule? Or are we getting confused because that's using Y's and X's and this is using X and Z?
Wait, what
we
does
get
free
that.
occurrence mean again?
Free occurrence, okay, perfect. So in this formula, a free occurrence is, it's one that's not bounded, and you have to bound it with a quantifier. There's no existential quantifier on this, there's no existential quantifier on this. An example to help your intuition, x less than 3. X in this case is a free occurrence. In other words, you can't say if this is true or false, because there's a free variable in there. If I were to bound it and say something like there exists x, such that x is less than 3, now this is no longer a free occurrence. This is now bounded by this quantifier.
Since it says
And now you can determine if this statement is true or false. Good?
Yeah.
So you can't determine if this statement is true or false. Ah, this one you can. Good?
Yeah.
Any other questions about that? Okay, so that's universal specification. That's going from for all elements to an arbitrary element. And then our next rule is our rule of universal generalization. And this is going from here to here. So, from a formula S, so now in this case, here's S, and here's R. Once again, R is just this piece of it. It doesn't include the quantifier. Okay? So let's read it. From a formula S, this formula, we may derive a formula, oh, we're not using S. Or we're not using R. From a formula S, we may derive for all y, S, provided that the variable y is not flagged in S. And we didn't talk about flagged. I can't believe I didn't write that as a side note in between here. Sorry. A flagged variable, we'll see an example of it here in a second. But a flagged variable is a variable that's freed and introduced in a premise. So notice that in these two premises, we didn't have any free variables. They were bounded.
No,
So we didn't have any flagged variables.
those were not bounded, it's for all x.
Yeah, so you're thinking about bounded as in
There's a specific.
some, like you're thinking like a greater number, some limitation in like a domain or range sense. A bounded variable is one that a quantifier applies to.
Yeah.
Notice that we can determine, so let's look at our example again. X less than 2. We can't call that true or false. But if I put for all x, x less than 2, now this x is bounded.
Right.
Now I can determine if this statement is true or false.
Right.
So this is, if I introduce this as a premise, this is a case where the variable is bounded. But if I try introducing something like this as a premise, which you'll see that we have to do when we do conditional proofs, when I introduce something like this as a premise, now this is a free occurrence of a variable. And they're going to call that flagged.
Why is that important?
That it's flagged, that you can't generalize this. So imagine that you were doing some proof about some number less than 2,
Okay.
right? So you had some proof of the form, if x is less than 2, then, and you were doing a proof, okay? So you introduce x less than 2 as a premise. It's a conditional premise, right? But you introduce it as a premise. Now imagine you tried to generalize. And you try going from this to, for all x, x less than 2. No, bad. You can't do that. It was perfectly valid to do this to this.
Because it was bounded.
Yeah, it was bound to begin with and we rebounded it basically. But to go from this to this, that's a big no-no. You can't do that. So when it's a flagged variable, you can't do this. If it was introduced in a premise,
False that way.
huh?
Because it could be false that way.
Yeah, because it breaks our second criterion.
So a flagged variable is a
From true premises, we should only be able to come to true conclusions.
Not the first.
What if the start of this was there exist x?
Oh yeah, it might have been the first one. Huh?
What if the start of this was there exist x?
Up here?
No. Because that way it would be bounded.
You're saying right here?
Yeah,
It's already bounded. There exists x, still makes it bounded.
right. But then it's still not flagged.
Right.
Yeah.
Correct, it's not flagged.
So you could say for all z.
No.
For all z, there exists a z such that, sure.
This is only by
Look,
universal quantifier.
You can do what you're saying, so watch. So if I want to, it's just, you're going to see how useless it is. There exists x such that x is less than 2. For all y, there exists x such that x is less than 2.
Yeah, but that says you can
Sure.
That says you can take for all y and put it right before s. We may derive for all y x.
This is now your s. This is a formula that you're applying it to.
Well, not in our first one.
What do you mean not at first?
Okay, number one, we didn't apply for all x.
We weren't using this rule. We were using this rule. This rule says you can take s And as long as it doesn't have 5 variables in it, you can put a universal quantifier in front of it.
Yeah, what I'm saying is, say 1 was for all x, A implies, or there's this x.
You're saying if this was for all x,
The
there's
premise
this.
of my point is,
Let's do a more complex example
okay,
and then see if that sheds some light. Because I just introduced it without giving us an actual example of it. So, go ahead.
Flagged is a free occurrence that isn't a premise.
It's a premise with a free variable.
And the variable.
Then that variable is a 5 variable. We didn't have any free variable. These were only 2 premises in this argument. In both cases, they were bounded. We didn't have a free variable.
Okay.
I'll do a proof here real quick where we will have a free variable. Because we're going to be doing a conditional proof over here.
Okay, and you can only use the rule of universal generalization when there is no flag.
When there's no 5 variable. When the variable didn't come from a premise that was, where it was a free variable.
Okay.
Okay? Good? Alright, let's do this example and then have more discussion if there's still questions. So let's start by symbolizing no ducks are willing to waltz. So that's going to be something like for all x,
dx implies w.
dx implies not wx.
Yeah.
And we'll actually do this one all correct. 2. No officers are unwilling to waltz. So for all x, you okay with me not switching between x's and y's? Or would you prefer I switch?
It's just fine.
Why would you need to switch?
You don't need to, which is why. But if it's confusing to keep using x's, I just want to communicate clearly. Okay, so for all x, officer applying to x implies willing to waltz applies to x, right?
unwilling, not willing.
No.
No unwilling.
Officers will always waltz, ducks will never waltz, is what we're saying. If you're a duck, you won't waltz. If you're an officer, you will waltz.
Oh yeah, right.
Good?
No implies no means.
No implies no means.
No, it's-
I know what you mean.
No officers implies unwillingness, implies officers are willing.
So it doesn't.
Right. There does not exist x such that O applying to x, or such that not O applying to x implies W applying to x. And then distribute through the negative, makes this positive, and switches that to for all. Yeah. Okay, anyways. All my poultry are ducks.
What's poultry?
A bird.
Why do you know that?
Why do you know a canine's a dog? For all x, my poultry applying to it implies duck applies to it. That's a premise, that's 3. Okay, now we'll do the rule of dropping the quantifiers real quick, and then I'll come back and introduce.
This isn't a conditional proof, is it?
Yes, it is. Yeah, what is this part saying? None of my poultry are officers. It's saying if it's my poultry,
And it's not an officer.
then it's not an officer.
Mm.
So we're going to ultimately have px implies not ox. Okay, so there we have that. Let's drop the quantifiers. 4, we have dx gives you not wx. 5, we have ox. Maybe I'll make my O bigger. Ox gives you wx. 6, we have px gives you not wx.
That's,
And this is,
wait a minute.
Yeah. Where'd you get
It's
the
not.
X does
It's not W. It's
oh, thank you,
dx.
dx.
And just the x.
Okay, good catch. And then all of these, let's see, this is universal specification on 1, universal specification on 2, universal specification on 3, and this depends on premise 1, this depends on premise 2, and this depends on premise 3. Wow,
You botched it up.
yeah. Doing these brackets and thinking 3 at the same time is not computing in my brain. Okay, jeez, I was about to do it. Now, our conditional premise. And this is where we're going to have a 5 variable. So we're going to do 7. We're going to do px. Let's end it like we normally do for conditional premises. P applies to x, and this is a conditional premise. And it is line, what number am I on?
4.
7.
Oh.
Just depends on itself, right? And now, this is a 5 variable. It's a free occurrence, and this is a premise.
You're throwing this premise in?
Yeah, it's a conditional proof. Ultimately, I need to show P of x implies not O of x.
Right, just like how we always do.
Yeah. So now we can start doing proofs exactly the way that we're used to. P of x gives me D of x.
D of x is true.
So I know that D of x is true.
You know, not W of x.
And this is tautologically implied by 7 and 6. And now I'm using premises 7 and what? 3?
3.
Thank you. I cannot do that. Alright. 9 is, since we know dx, what do we know?
Not W.
Not wox, but not wox also implies not ox.
Why not W O X?
Why not WX?
Dx implies not wx.
Right.
Okay, let's just do it one at a time. So we have not wx is tautologically implied by 8 and what? 4. Thank you. And what premises did I add? I had 7, 3, and what did I add? 1. Just can trust you guys on that. Okay, 10. Now we have not wx implies not ox.
Right.
So now we know not ox tautologically implied by
6.
9 and 6,
No.
5, right?
Yeah.
And now I'm using premises 1, 2, 3, and 7, right? And now I can come back down to 11, finish my conditional part, and say px implies not ox, right? And this is, and we went from 7 to 10, and now we're not using premise 7.
Still. Yes.
So now we don't have a flagged variable anymore.
Do you have to say conditional premise after 10, or can you just say 7?
Just make it clear what you're doing. I don't know what he does.
I still don't understand why you're able to say, now we're not using premise 7.
Because how would you have come to that conclusion?
Because you say
We've
if.
done this so
I
many
know
times.
that. And every time I just pass it by.
If your premises imply A implies B. Sorry. Oh well, we're going to do logically equivalent. Here's where we're going to end. I'm doing it backwards. This is logically equivalent to your premises and A implies B. These two are logically equivalent. So if your premises together with your antecedent gives you your conclusion, then your premises give you the implication. They're logically equivalent. Right? So, if our premises together with our antecedent
So,
gives us a conclusion, then our premises alone give us the implication.
Okay.
Same thing we've done
Yeah, that's a tautology right there.
a billion times. You didn't do your homework. Otherwise, you would have done this so many times.
And I probably would have just done it. without
Okay.
knowing why that works.
And now we need to use our new rule, universal generalization. Right? So now we can finally say 12 for all x. X being a poultry implies x is not an officer. And this is universal generalization on 11. And it's using premises 1, 2, 3. So we prove that this is true from these three premises, which is exactly what we were trying to do.
So what did a flag variable have to do with anything?
We couldn't apply this rule until we got rid of premise 7.
Because that was our.
Anything you can't flag, so let's go back to a flagged variable. A variable is flagged if it relies on a premise that has a free variable in it.
Oh.
So x is flagged here because it relies on premise 7. It's flagged here because this relies on premise 7. Flagged here because it relies on premise 7. Flagged here because it relies on premise 7. We're no longer relying on premise 7 that had the free occurrence of x. Therefore, x is no longer free.
Right.
And you're used to this kind of thinking when you did proofs.
Mm-hmm.
You said something along the lines of, let x in the set, therefore some other element in the set, therefore anytime x is in the set, the other elements in the set, therefore for all things in the domain it implies, I don't know, whatever we were doing.
Right.
But you do that all the time. You do these mini conditional proofs inside your proof, and you understand that you were just talking about some specific thing that you couldn't generalize on. Hopefully you understood that. Okay, so any questions about the proof? Or any question? Let's just make sure both these rules now make sense. Sorry about the flag. Hopefully that now makes sense. I should have had a better discussion about that before I introduced the word.
Well, can you just like write a definition on the word so we have it later?
I don't know that gives a definition, but I don't want to write it out either.
Okay.
A variable is flagged in any formula if the formula depends on a premise
That it is not bound.
that has that variable, that has a free occurrence of that variable.
Oh, it has to be free, not it's not bound.
Yeah. This is the only time that we have a premise with a free occurrence of a variable.
Right.
And this could have been something along the lines of px, or there exists x such that, and some other statement about x. We still have a free occurrence of the variable in here, so it would still be flagged from there on out. Good? Although I can't think of a use case for that. I'm sure we'll come across stuff. So we're good on that? No more questions? Okay, then let's just do another one. Over here, this example, no Episcopalian or Presbyterian is a Unitarian. John Adams was a Unitarian, therefore he was not Episcopalian.
Alright, this is the inclusive one, so.
Good? With
Okay.
wrapping your head around what we're doing? So we're trying to show that John Adams was not Episcopalian. So let's see, what's our first line saying, our first
Do you
premise?
even need Presbyterian?
I would do.
Well, we have to do some,
Isn't
we
it?
have to,
Uniform.
what's the word he uses? We need to symbolize our premises. And you can't just throw something out because you're looking ahead and saying, I don't think I need that information.
Uniform implies not Episcopalian or.
So for all x,
Yeah, for all that.
EX or PX?
Mm-hmm.
EX or BX.
I would say UX implies.
Implies UX.
EX
Not
or PX implies not UX.
Right.
Right?
Yeah.
So no Episcopalian or Presbyterian is a Unitarian. 2, we have John Adams was a Unitarian. Maybe we'll wait to introduce that one for a second and just do dropper quantifiers. Oh, sorry, this was a premise and it only depends on itself, right?
Mm-hmm.
2, let's just drop it. So we have EX or PX implies
Not UX.
not UX.
That's US1.
Yeah, this is, do I do the US first? Universal specification on 1. These only depend on 1. And maybe we'll just keep messing with it a little bit. 3, I'm kind of looking ahead, but I'm just gonna write the contrapositive of this real quick. So from that, I know that UX implies not EX and not PX.
Right.
Maybe put parentheses in case any part of that's confusing. And
The
that's just
answer
tautologically implied by 2.
Why is that?
Think
When you
about-
distribute a negative, it changes your ors
Oh.
to ands.
But also, just think about the statement. That's what it's saying. That's what I tried to get Nani to do at the start. UX implies not EX and not PX.
Anyways, so this still just depends on 1. And now we can introduce our next premise. We know that U applies to A
Mm-hmm.
for atoms, right? This is a premise, only depends on itself.
Oh, here's our.
Now, is A a flagged variable here?
Yes.
No.
It has no. It has no quantifier applying to it.
Has no quantifier, so A has to be a free variable, or
A flag.
a flagged variable, right?
Yeah.
Mm-hmm.
I know you're trying, and then the answer's no. We know, but.
And the answer's no. Why is the answer no?
I don't know, but
Because that's not a variable. That's a constant. Remember your terms.
Adams.
Your terms, you have variables and constants. John Adams is a particular person.
Right.
It's not an arbitrary person. It's a particular person.
Just
Makes
like
sense?
Elizabeth in my homework.
So this is a constant. Adams is a constant. This is not a flagged variable.
Okay. Makes sense.
Good? Now, we know
But we're still gonna have to pull it out since it's a condition.
5,
Oh, that's just a premise.
we know that not EA and not PA. And that's tautologically implied by 3 and 4.
Mm-hmm.
Now we're using premises 1 and 4.
So
You good with that?
since X is for every person and Adams is a person, you can put A.
Yeah, X is true. This is true for any arbitrary element.
Right.
Here's an element. If it's true for any X, it's true for A.
Right.
Good?
Okay.
So notice that when we're done with this proof, I mean, we're talking about proving something about a particular person. We're not going to have existential quantifiers because we don't need them. You only need quantifiers for variables. Right? There's a huge difference between determining if this is true.
You've been programmed.
Huge difference between determining if this is true and this is true. I am broken. Alright. This one, we need some sort of quantifier on the front. This one we don't. So when we're done with this proof, obviously we have one more line to go, but we're not going to have any quantifier. So 6 is just, which one we were doing? Not Episcopalian. Not Episcopalian applies to Adams. Logically applied by 5, and we're done.
So since it's not and not, then obviously one's true.
Yeah. I can't remember the name for the rule.
But yeah.
But if you have A and B, that implies A, or A and B implies B. Good? Any questions? You see the big difference between what we did here and what we did here?
Yes.
Here we were always talking about some arbitrary element.
We didn't have a conditional proof or conditional premise.
We didn't have a conditional premise, but the point is getting comfortable with this was a flagged variable.
Which
We ended up getting rid of the flag variable, and then we generalized because it was still a variable. Here, that doesn't even make sense. So that wasn't flagged. And even though it's not flagged, we still can't generalize because it's not a variable. I mean, we could generalize if we wanted to, it just doesn't make sense because the way you would generalize is you say something along the lines of,
For every John Adams is it.
no, you say for all people,
Right. We're John
not
Adams.
being an Episcopalian applies to Adams.
Yeah, that doesn't make sense.
Well, it makes sense, it just doesn't add anything.
Right. It doesn't make.
It's like saying for every x, 2 plus 2 is 4.
Right.
That statement has nothing to do with x, but sure, it's true. For all people, John Adams is not an Episcopalian. Yep. Doesn't matter who you're talking about, he's still not. All right, good?
This statement is false.
It is? Is that statement true or false?
Oh well.
It's not even a
I
statement.
was wondering why you wrote that up there.
I didn't write that for this, I was having a conversation, just wrote it.
You have a conversation with
I saw that and like, but
No, Michaela, this statement is false. Was that statement true or false?
It's not even a statement. Or a.
it's not Donnie Salt's
It's
argument.
not a
That's not a sentence? How is that not a sentence?
Because it can't be determined true or false.
Yeah.
It's self-contradicting. In saying this statement is false, you're saying it's true. That's like saying the sky is red and not red in one sentence. It's a self-contradicting sentence. And that's what we were talking about. Self-contradicting sentence, and I wrote that up as an example.
This statement is false means it's true.
If you're claiming the statement is true, and the statement is claiming it's false, so in one line you're saying it's true and it's false. Self-contradicting.
Validity of the truth is false.
It's like people that say truth is subjective. And it's objectively
Who
true
says
that
that?
truth is subjective for a lot of people.
Okay.
Liberals.
Yeah, and when you get to the far left, they have all sorts of crazy ideas. Like, logic is a power structure put in place by white people to maintain power. I like how they try to use logic to logic, but you can't use logic.
I don't know why this bugging me, but I'm sure it doesn't.
That's fine. Okay. Okay, so now we're to some exercises, and there was just one exercise I wanted to do.
How many sections are in this chapter?
Do we do? Oh yeah, that's one we just did. Okay, so exercises. Here's the way that this works. This exercise works, and I'm going to make all of you do a problem. So be ready, because I want to get real comfortable with this kind of thing before we go on. And I like the idea of you realizing. Here's basically what we could call axioms. Here's a couple definitions, and we're proving things from here on out. So let's make sense of this. Yeah, I think it'd be fun. So, geez, that's quite a mouthful. Okay, in the theory of rational behavior, which has applications in economics, ethics, psychology, the notion of an individual preferring one object or state of affairs to another is of importance. We may say that an individual weakly prefers x to y if he does not strictly prefer y to x. Okay, so I think the Q here is going to symbolize weakly prefers. And we're going to use the P here for prefers.
Strongly.
Strongly prefers. Yeah. And then I is going to be indifferent. If you're indifferent, they're on the same level basically. Weak preference,
Strong.
and then strong preference. So let's go back to where we were. We may say that an individual weakly prefers x to y if he does not strictly prefer y to x. So he can weakly prefer x to y if he doesn't strongly infer y to x. That's what this is ultimately going to be saying. He strictly prefers x to y if he doesn't weakly prefer y to x. We use the notion of weak preference for formal convenience. I feel like I read that wrong. We use the notion of weak preference for formal convenience. For if we use strict preference, we also need a notion of indifference. Okay? So we're using weak preference because we've either got to use these, I'm guessing, or those, I'm guessing, and he wants to introduce those as definitions. The point of the present exercise is to ask you to show that on the basis of two simple postulated properties of weak preference and the appropriate definitions of strict preference and indifference in terms of weak preference, we may logically infer all expected properties of strict preference and indifference. Let's use Q for weak preference, P for strict preference, and I for indifference. And then we have our two postulates. Maybe we'll read it in words since you take time to do that. Our two postulates or premises on the predicate Q for weakly preferred just say that it is transitive and that of any two objects in the domain of objects under consideration, one is weakly preferred to the other. Okay, so here's our two premises. Our premises are saying if x is weakly preferred to y and y is weakly preferred to z, then x is weakly preferred to z. Right?
Right.
If you have some preference of x to y and some preference of y to z, then you have some preference of x to z. And then we're saying either you have a weak preference of x to y or you have a weak preference of y to x.
There's no in between. But didn't you just say that indifference is a thing?
Well, strict preference means they have to be ordered, one over another. Weak preference could be, I'm not sure, or yeah, I guess this one. Okay? Let's look at how he defines indifference so you can get it. If you weakly prefer x to y and weakly prefer y to x, then you're indifferent.
Oh, right. Okay.
Good? If you can go either way, you're indifferent.
Right.
You strictly prefer x to y if you do not weakly prefer y to x.
Right, obviously.
Make sense? So these are two definitions, and notice that we define them in terms of Q. Okay? So we have two premises, and then we made two definitions based off those premises.
Okay.
I defined what it means to be xpy. It means not yqx. I defined what it means to be xiy. It means xqy and yqx.
Didn't he define that in his...
It's just like defining subtraction in terms of addition.
Right.
So you might have two axioms that give you addition and multiplication, and then you might define subtraction and division in terms of addition and multiplication. That's kind of what we're doing here. So we only have postulates about weak preference, we only have axioms about weak preference, and then we use those same undefined terms, Q, to make definitions from there on out. If you remember back to geometry, for those of you that took it, our axioms, remember, we had to start out with undefined terms in our axioms.
Yes.
For example, we don't define a point in geometry. It's kind of what this Q is here. We don't have a definition for what that Q is.
Right.
But now we do have a definition for P and I in terms of that Q. Just like we came up with definitions for objects in terms of points. But we didn't have a definition for a point. Make sense? So same kind of thing. And so here's our postulates, here's our two definitions, and we're going to prove this list of things.
Great.
So you're gonna pick one and you're gonna do it, and we're gonna check through 'em.
X such that
Do you need me to do one first to get things rolling, or do you feel like you can just start?
Just get ready to.
Oh, that's right.
You want to jump right into it? All right. Come on up. Pick one.
Pick one.
Sorry, they're probably kind of hard to read from there.
Yeah.
Write what you're doing, so decide right here, so that we can see it on the camera and make sure it makes sense when we watch later, and then we'll see that worked. And that way it's a nice cush class where I can just sit down the whole time.
Says right here, right?
Yeah, continue from there, but just write what you're trying to prove to the side right here for the camera.
Oh yeah.
The conclusion that we're going to get to. And then we'll just keep erasing, because you can only start with the 1, 2, 3, 4 for whatever you're proving.
we can use two obvious.
Wait, did I write that down right?
Yeah, because both those are impossible. You can't have xpy and ypx.
YPZ.
It implies xpz, I assume. That's what makes sense.
Yep.
Alright.
We already have that, don't we?
No, we do
Oh,
not.
we have Q's.
He's got a ways to go.
Okay.
So we're gonna, I don't know, are we gonna introduce P in our proof?
Here's your two premises.
Mm-hmm.
You can use either of those as needed. And then these are definitions.
Probably.
These don't give you new information. They just help you rewrite this information.
1 and 2 are your two premises.
Yeah. So you can use 1 and 2 to your heart's content.
Also 3, because we know.
Yeah, 3 and 4 are just definitions. You can't start with 3, because you don't have anything to use it on.
So probably drop all of your universal quantifiers for 1 and 2, right?
I need a conditional premise, right? I'm going to say this and this as a premise.
Yeah, you're going to need to get to a point where you have x, py, and ypz as a premise.
Well, I can do that right now, can't I? Do I need to do anything before that?
Yeah, drop all
You
your
can do that right
universal
now, but
quantifiers.
understand you're creating a flag variable.
I can get rid of that later though, don't I?
You can.
Okay.
Yeah.
Okay, stop me if I'm doing it wrong.
Well, I don't know how to do it. I mean, I just start doing what you're doing. See how.
Yeah, you probably already have the whole proof in your way.
Dottie, aren't you supposed to drop your universal quantifiers first?
You didn't want to do that first. You wanted to introduce a premise. That's fine. You can introduce a premise at any point in a proof.
Oh, I see what you're saying now.
Yeah.
Well, I guess, yeah, I can do that. Either way. So drop the quantifiers from these two,
Yeah.
basically.
Sure.
Okay, how are you
He's gonna use his condition for solve.
Oops.
Yeah, but how would you use that premise to get that? I don't get it.
X, P, Y is true and Y, P, Z is true.
So,
Do I need to do my
how do you
brackets
write
off to the side?
from x cubed y?
You can just do it from there on out. Just make sure 5, you know what 5 is using 1, 6 is going to be using 2, and then go from there.
Are you also gonna have to drop the universal quantifiers
So
for 4?
is he going to have to prove that
Hmm?
not, so he's going to say that not y cubed x is x p y. There's something that's included.
He's going to show that if x is preferred to y and y is preferred to z, then x is preferred to z.
And before it was weekly.
I know, I'm just trying to want him to get this
once he
find out.
introduces his conditional premises and starts working,
It'll
with
make
it,
more
fly.
sense. It'll make more sense as soon as I start substituting.
Look, all he's going, you keep going. You got a ways to go before you start plugging in. All he's going to do is introduce this part as a premise. Plug in his definitions once he drops off the quantifiers off those sides. He knows that he can do that. And then rework what comes out till it looks like this. Right?
He's gonna have to use 3 and
Because
4.
xpy is the same thing as not yqx. And ypz is the same thing as not zqy. So he's going to have not something and not something. Then factor out the nots probably to get something or something. So he introduced that as a premise. And then he decided not to drop the quantifiers off these and just use it, which I'm fine with. Technically, no, but
Why?
we all know what you would do.
Why can't he
You
do
would
that?
have to use US3, US4.
Because you need to use a tautological implication. We can't do a tautological implication on this or this.
So should I go back and do that?
No, you're fine. We all understand that he just used a definition going from here to here, right?
Yeah.
Okay.
You're saying he was supposed to do what he did on 5 and 6 to 3
yeah.
and 4.
Yeah.
Okay. Yeah.
Aren't you supposed to change that to 4 if you're not?
I just follow the definition.
He didn't not anything
Oh.
yet. He just used the definition.
Okay, trying to get to x, y, z. And this is,
Yeah,
I'm
I know.
gonna little scratch word. This is not z,
Not
q,
Y,
x.
Q, X.
Is he even gonna use 3?
Probably not. I'm not gonna have an I anywhere in here.
How did you get not ZQX?
It's the same.
That's the same thing using the definition. He's saying once he gets this, then he has this.
I'm trying to get
So
this.
he's just working
I'm
backwards.
using this to get to there.
Oh, I
It's a
think-
common
how'd you
strategy.
get not
We call it
ZQY?
unraveling your definitions.
Huh?
Oh, you're saying from here to here?
Yeah.
He's using the definition. What does xpy mean? It means not yqx. That's the definition. xpy means not yqx.
Yeah, but and then not ZQY.
Same thing. ypz is the same thing as not zqy. Put a not, flip the order, go from p to q.
Yeah, so I'm gonna use number 1 now.
Do you see how he's using those definitions?
I don't see how he's using number 4. No.
Okay, so I have this. xpy is defined to be not yqx. So all I'm doing is substituting, switching it out. I'm doing the same thing with this.
Sorry, the camera.
He's just using different variables. Get rid of the variables
Right.
in the.
Right.
You good now?
So you're just using ZY instead of Y and X.
Yes. That's what he's doing.
Yeah.
Now I'm going to use this. It's going to be
No, you're gonna want to get 2 first,
2.
and then use 1, right?
Yeah. Don't you?
What do I need to do?
Don't
Use.
you want to get rid of the knots first?
Yeah, I do.
So it'd make not XQY.
Not X, Y, Q. Not
Oh, that's
Y,
not.
Q, X.
That's not N. That's an
Or.
or.
That's yeah. Yeah, I don't see why I would need to use 2. What is 2 even saying? Oh.
X is
okay.
weakly
I
referred
already
to y,
used
or
two.
y is weakly
Yeah,
referred to
I
x.
already used 2. So what I need is to do this.
But my point is, once you take out that knot, then you're gonna be stuck with 2,
Why?
because it's gonna be or.
This is an and.
Well, you take out the knot,
Same
then
if you
it
factor the
flips,
Oh.
then it
Then
makes
it
it an
replaces
or
it to
statement.
an or.
So I can probably do it with the knots, can't I?
You could probably what?
Can I do it with the knots in there?
Well,
Do what with the nots in there?
Use this.
yeah.
It would be, I don't know if that helps me at all though. That would be
You can't do it.
Well, one way you can rethink about this, remember that's the same thing as, so A implies B is the same thing as not A or B.
So that's the same thing as,
Don't you have it though?
Have what?
So just take A and then goes implies not,
So are you in the right order?
not X, Z.
I don't know what you're saying.
So right here, where was I looking at? So right here, then you could go both ways.
here's what I need to do. I
Right,
need
we
to show
already
how
used
this-
it one way. We
I
don't
need
want to
show
go
how
back
this
where we
is
started.
equivalent to this.
Well, isn't this, couldn't you just do implies not, X weekly Z?
What?
That's what I'm trying to do. But I can't go directly there because this doesn't line up with this.
Yeah, it's not in the right
I've
order.
got to somehow get this and this to equal the same thing.
Yeah,
Show they're equivalent. and
That's
then I
not,
can
that's not A. You know what I'm saying? Use what Donnie just said. A implies B, let's use that for number one.
So what I want to do is I want to see what not this equals.
So not even N creates not over N, not
It
or.
would be,
So
it would be
not X, Q, Y.
not x, q, y,
Or,
or
not
No.
Y,
y, g, z.
No.
which is
No,
Y.
that's
It'd
not
be in
true, that's not
parentheses, you're distributing
Yeah.
different.
It'd be in, that'd still be
So
an
it'd be
and
not, it'd be not parenthesis, X weekly
Yeah.
implies Y, or
well, we
Y,
just like-
E,
we just skipped
Z.
a step, guys.
I've got to
Yeah.
distribute that. I distribute that by doing this.
I can't see your end, so
Not
these guys
X,
keep
Q,
track
Y.
of
Not
it.
a or b is the same.
That's an or, not an and.
Whoops.
Wait, he just distributed.
Yeah, it is. That's an and.
It's an N.
No,
Yeah, that's an and.
Okay.
you're flipping it, you're flipping the,
That's what you're supposed
He
to
has
do.
it distributed,
I haven't done that yet.
yeah.
okay, I'm confused because I thought you take this, and the moment you take those two out, it flips that to an or. Because what this is you're just taking those out.
Factoring it out flips that to an or, if that's what you're trying to do.
Yes,
Yeah.
factoring out flips it to an or.
That is correct.
That make it true.
But you guys keep working on this. I'm just gonna start doing some scribble work to the side.
Okay.
Don't mind me.
Slowly writes down the answer.
That's continue your train of thought like we were doing.
I want
So
to.
factor out
This
those
is going in the
knots.
right direction.
I'm not. That's not where I
Well,
want to.
just start, factor out the knots.
1 second. Those are the same thing. Where does it say they're the same thing?
Number 3, 4. Oh wait, no, never mind.
They're not the same thing.
X is weakly preferred to Y. Y is not weakly preferred to X.
X is weakly preferred, or Y is not weakly preferred to X.
But it doesn't.
No.
Is that the same thing?
Doesn't
I
say
think
you
that's
can
the
do that
same thing.
anywhere.
What?
Doesn't say you can do that anymore.
No, it doesn't.
He might just need to figure out his preference.
I'm just trying to think about it.
Yeah. I don't know.
Implies. A implies B. But not A. Or B. Oh my goodness. Look. So, this is what I'm thinking.
A? Wait. Okay, go ahead.
Okay, so. A implies B, right? So, not
On
A. implies B. What does that get?
No, not A or B.
Not A or B.
Or sorry, so the minute you not A, which is this, or once you take those out, then that's nodding A, right? No.
I see what you're saying though. I get where you're trying to go.
Yeah, I don't know why we haven't just gone down the rabbit hole yet. Let's just go down one of these.
Good. Okay. All right.
So,
I have a
to
question
the
real
side.
quick.
To the side.
So you're saying take out my nots, basically,
YQX and or.
or
No, that's not what I'm saying.
No, those are the same.
that's what you just said.
No, let's go down this rabbit hole.
Which rabbit hole?
This one. What does this really mean?
Oh, okay. So not
That's what I was thinking.
not
I was thinking take this
XQY
out.
or
Not YQZ.
no, it's still in until we distribute it.
Oh, well, let's just distribute it.
YQZ. Well, I'm trying to make sure I make no mistakes.
Implies B.
And no or B, which is XQZ. This is going to be not XQY
Which is really
or
this.
not YQZ.
What do you do with three ors? They all could be true.
Levi,
Hmm?
and then it turns into that. Then you can turn it into
Then
that.
not X.
Not YQX. Not YQX. So this turns into
So not YQX
One
turns
second.
into XPQI.
turns into YPX. YPX or ZPY.
I don't know
Or
what that gives you, but
XQZ. What does that tell us?
Wait, why did you get Z?
Growth parentheses.
Oh,
we're dealing with Z the whole time.
oh.
We're trying to get not ZQX.
That doesn't really. Oh yeah, it doesn't even.
That's where my brain was going.
These.
That's as far as I got.
Okay.
Was that point?
We need this to be false, which means we need because.
Well, look,
ZQ.
you made this a premise, which makes it true, right?
Yeah.
And then this is the opposite of it, right? Oh no,
No,
it's
it's
not the
not.
opposite.
This is
It's the same thing. Oh no.
No.
It's
No,
just
it's
Andy instead of
switched.
or.
Yeah.
So good.
So if that didn't work, I have.
Does-
Wait a minute. We could. Maybe we do need to use this. I don't know.
Of course you do. Why would they give? Oh, I guess
For
each-
the other problems.
Right.
That's still not useful.
Is ZPY the same as YPZ? Or are they two different things?
no, they're
different.
different.
Okay,
Different.
so
Because Z is
you
preferred.
could do, so there's so many different options that you can
If it's
Well,
not
why
grounded
don't-
for this
why don't
long,
you
I don't
change-
know if we can even.
Why don't you change your original formula?
What do you mean?
Why don't you make it a contrapositive?
Well, change these so that when you get here, these are switched.
Well, what he did is he took his first
So
premise.
that you get back to here.
I don't understand.
He took his first premise and he used his first premise.
Yeah.
Oh, that's true.
Mm.
You can't.
Or
change.
all.
I'm looking at the textbook.
Oh, this is homework.
I feel like there's a role we're just missing. Quantifiers applies and conditional
That's what we're working on right now.
methods.
Such a broad role. Applied
Okay,
applied
why
methods
can't-
are very.
if using that first premise.
There is no trick to proof. You just gotta prove it.
Can't you just say?
I remember you saying, first thing you do, start
why-
with your
Can't you just say y cubed
premise.
x And
Keep your conclusion in mind under alpha definitions. And
I just
middle.
think you can switch the variables. Put them in different places.
You can't. You can't take xqy and make it yqx. Those are two very different statements.
Well, not if you do it without the whole thing though. If you make it the same statement.
What do you mean?
So
You
you're
say
not
let
just
them be
taking
equal?
one and you're replacing it, but you're switching them throughout the whole thing, so it's saying the same thing. You're just switching the places.
If it, what you're doing is very, very, very dangerous. Take the predicate likes. Leah likes Donnie is a much different statement than Donnie likes Leah. Those aren't close to the same thing, and you can't just go around switching.
Okay.
So that's a dangerous thing to do. There might be cases where it happens to work, but it's definitely not a rule you can follow.
Not QZ is the same thing as what? Where do you go with not QZ? Or not ZQ? Not
You could
ZQ,
try
right?
looking backwards from the conclusion.
That's what I'm trying to do. I don't know how to do that either. All right,
Well,
let's
just
try it. Let's
transfer
look at
that
it.
using before.
This turned out to be not useful.
Bravo.
Let's
Down
go.
the wrong room.
So go.
Let's go like this.
That's happening.
XPY and YPZ implies
XP.
not ZQX. And then this changes out to not YQX and not ZQY not or not ZQX.
Wouldn't you not that?
And then we can just do this. This turns into YQX or ZQY or not ZQX. Oops. See? I feel like that's more promising.
Okay, now how do you get,
And that gives us
Number 3. It gives us something about number. Oh no, it doesn't.
this seems like it should be so simple. Why is it? Why is it not simple?
I
Well,
don't think
didn't you-
it seems
didn't
like
you
it should be
have
so
to-
simple.
Intuitively, it's so simple.
Didn't
If
you
you
just
prefer
get
x to
that,
y
though?
and you prefer y to z, then you prefer x to z. That
wait,
makes
didn't
total
you just
sense.
Right.
skip that though? Right there?
Yes. Yeah, they're the same. They're the same. So we can. You're right. No. Well, they're not quite
You
the
got
same.
something. No, they're the exact, this is exactly the same to this.
But there's a not there.
Yeah.
What's
so-
the?
So I'm looking at Donnie's scribbles and he's trying to do what we're doing and nothing's working out.
What if we do this?
Oh, it's pretty good. I got one more connection to make.
Not YQZ and not ZQY implies not ZQX, and we have that. That's exactly what we. It's exactly what we're doing.
No, it's bored now, isn't it?
No, that is the exact same.
Okay, wait, what
If we
did
just
you say?
overcomplicate it,
Oh, you're right, because it's not A.
that
It's-
can't make sense.
Wait, what? It's not A or B, right? And then
I
you
don't know.
went from A
Well,
implies
I
B.
just took it from here. This is what we're trying to prove. So obviously that makes sense because yeah, that's what we're trying to prove. Now I have to turn this into that simple.
Wait, look.
No,
So you went from this to this, right?
I want this to this.
Well, I'm saying you can go from here to here.
Yeah. It's the same thing. They mean the same thing.
Yeah, he needs to figure out
I
why.
have to figure
He
out
needs to
how
figure
to
out why
get this.
this implies that, right?
Yeah.
Which
And
is yes, why.
So basically I have to do this, but I don't know how to just throw that in there. It's, I have to use one of these
Use
premises.
one or two. Well, then start looking at things. You know what I'm saying? Just start looking at
Can't you create a conditional
it.
premise
Okay, you have to use premise one.
Z
Oh, you already
I
have
already-
x. You already used
or
it.
ZPX?
You have x, y, z, q.
1 second, premise 1. xy and yqz, xqz. Why did I do that? That's exact, why did I not do that already?
It'll bring you back, Levi.
Not yqx, not zqy, implies not xqz,
Yeah, I think that's how it works.
not xqz, chronologically implied
Oh, we just did it.
by 8.
We just did it.
That was that easy. That was
What?
that's true,
That's what
right?
I was trying to
Let's
say.
see.
This implies this.
Literally what I was saying.
That's what I was trying to
I
say.
didn't. I'm
at the
sorry, I
very
didn't get
start.
that from what you were saying.
Oh, you're wrong.
Like, this is the
You're wrong.
premise, this
What
is
are
how
you
it's
saying?
used, isn't it?
This and
Look.
this,
Look, it's
What
y.
they're trying to do,
It's
I-
y
No,
for x,
no,
not x to
no,
y.
no.
or is it z?
And
Is it
it's
supposed to
wrong.
be like this?
That's what I'm
No, look,
getting
it's
frustrated. I was
y.
like,
X to y, not
Can't
y
do that.
to not
So
y
that's
switch
the
it.
problem we're running into.
You can't just switch it.
Oh, you're right. But no, because it's a rule. It's not. I'm not manipulating it that way. It's a rule. If y equals x and x y, it's. This is perfectly valid. What I just did.
Levi, that's what I was trying to do.
I know.
And
I
he
did
was
not.
telling me I was wrong.
Well, I
You
thought you were doing something
can't
different.
do
I
that.
can do that
No.
because this is true.
Look, not y is preferred to x and not z is preferred to y. I mean, even if your logic about distributing the not, maybe that works. I still am questionable about that, but your order is completely wrong.
Why?
This
says
is x,
but
y.
this is for all.
Y, z.
Yeah.
Levi's saying we're not
It's
choosing.
coming from going to.
Oh. Okay.
I mean, you just flip the order, but then you're going from z to x,
Which is.
the opposite.
No, we're gonna be.
That's right, isn't it? Or unless no. Because what is it like that? I need. Is it not zqy or is it not z?
No.
qy?
Yeah, parentheses around the predicate
Okay.
in its terms.
All right. So that is not true. It was almost there. Almost there. So maybe.
What's the opposite of this? An and statement?
An or statement. If we were to take out
Pull out the knots.
pull out the knots, it goes
That's the opposite?
yqx or zqy. And that's not really what we need.
And what is this? What's this?
What do you mean?
What does this turn into? Can that turn into anything? Be transferred, like, is there anything logically equivalent to that?
Well, ypz. But I don't think that's going to help us get to our conclusion. The closest I got was we were going to have to use number 1 because number 1 has an implication. We're going to have to use number 1. And that's why I don't want to do this.
You
This turns
switch
into
these
or,
as well.
and I need an and.
You switch y and x.
These knots are throwing
Yeah,
everything
something
off.
different than what you did.
Got to figure out how to manage those without taking it out completely.
I know my marker's running.
Don't look at my work.
Okay, now
Keep going. I can't believe it took me that long to think of.
I feel like it should be not this hard. So
Yeah, it's.
something missing something.
Well, remember your premises. You have two of them. You're gonna have to use them.
So you're gonna have to.
So
use
we're
that
gonna have
for-
to use both of them.
So you're
Okay,
gonna
let's
have
see where
to
it leads us.
distribute.
Let's find out where it leads us. Just inked. Huh?
I think I like dealing with numbers.
This isn't helpful. I'll give you that hint.
Okay, so that's
However, we're gonna have to use both premises, but that's not helpful.
You said we have to use both premises.
Yeah, so think about it. If I know not yqx, what do I know?
X P
right.
X.
You know xqy! Wonderful.
Hey,
no.
No, you know. You know XPY.
What?
You know XPY, not XQY.
That's using a definition. Oh, maybe he didn't see what I thought.
Right here. Bro.
Oh, he did see what I thought.
Not YQX. Means you know XQY.
Oh.
You know that xqy or yqx is true.
Yeah.
If not yqx
Then
and xqy.
XQY.
And
Oh my goodness.
And YQZ.
Oh my
okay,
Obviously,
word.
that helps. Now what?
Then you use that. XQZ.
Okay, so you have xqz.
Wait, why do you know YQZ?
Okay, let's explain this real quick. So this premise says
That was so dumb.
xqy or yqz or yqx.
Y
Either x
or
is
over-
weakly preferred to y or
over
y is
that
weakly
because
preferred
of
to
the
x.
second variable. I promise
If y
you.
is not weakly
People
preferred
just-
to x,
I thought
then x is weakly preferred to y.
Okay, I got
That
that
is
one.
the-
And if
We'll see
z is
past
not
feature.
weakly preferred to y, then y is weakly preferred to z. Right?
Okay.
Those are saying.
So from there to there and there to there,
Okay.
using this premise, now he's doing it all in one go, is what it is.
Yeah, you.
And then he's applying this to
Wait, how'd you
here
get Y,
to get
Q, Z?
that. From
Okay.
this. Same as I think.
The exact same principle. Not ZQY, so YQZ.
You know either YQZ or ZQY. So if you don't have ZQY, then you have
Okay,
YQZ.
you're confusing me because you're pointing at XQY.
Same.
Okay,
Yes.
watch. I can rewrite this like
Substituting
this.
variables
I
into
can
one.
rewrite it as YQZ or ZQY. Same thing. It's just different dummy variables. It's saying for any two elements, you either have it this way or this way.
That's
It
how
says
predicates
for
work.
all X and for all Y.
Well, that's what this statement's saying. For any two elements you pick,
Right.
either
if
the
they're-
first is
even
preferred
if
to the
there's
second
one
or
Z.
the second is preferred to the first.
Okay.
One element, for any two elements, one is always weakly preferred to the other. That's what this says. And then this one
Right.
basically says it's transitive.
Right.
Okay, so that gets you XQZ. You're almost there.
XQZ leads us to not ZQX.
How?
For the same thing.
No. All we know
Oh.
is that
Right, because it could be true. It's not
we
exclusive.
know
right? It's exclusive.
XQZ or ZQX. Just because we know XQZ, just because we know XQZ doesn't mean we include not ZQX.
Right.
Not YQZ.
So I need to write down my opinion so that I don't do this wrong. This is from 2 and also 8. 2 and 8 premises
7,
7, 4, and 2.
2.
11. Well, I guess we can do that. And then or ZQX. This is from 10 and 2.
Well, you already knew XQZ. Why do you care about or ZQX?
Because we don't know XQZ. You just
We
said
do.
that.
No, I'm saying you can't conclude not XQZ from, or sorry, you can't conclude not ZQX from XQZ, is what I said. You had this, You got this differently.
Oh, so that's right.
This was a tautological implication of these two. I'm choosing this one.
Oh yeah, yeah.
So that's how you got here. You try
Not
going from
10 to
this
10
to
to 1.
not ZQX. That was a bad leap. You can't go from this to this. You can go from this to this, but you can't go from this to this.
Okay.
Right.
Right.
So you still need to figure out how to get that.
Yeah.
That's the trick. Here, you are.
Well, I think the part I gave you is a trick.
Here you go.
Okay.
This is 11. 11 to next line.
I'm getting out of work.
No!
I'm just gonna rewrite the numbers
Okay.
so that they're more lined up.
Is everyone just getting lost?
XQZ.
Yeah, just a little bit.
Alright, I'll re-go over it when you
No,
finish
I'm
this.
following you
Please.
very well.
Okay.
Was
I just
this-
felt like that was a big breakthrough.
Yeah, that's the first one. Now you need to use your other premise again. Do the weird mischief that you guys were trying to do but kept trying to do wrong.
So not. I'm guessing he's trying to say
everything's
A implies B is the same thing as not A. Well,
Okay. I think we need to go back to. No. We don't. Wait a minute.
Being
We
B
can go back to
implies not A. Oh my goodness. B implies not A, right?
Well, no,
B
because
or not.
XQZ is your B.
Or
A implies
B.
B
So then you don't
is
get
the same
not.
thing as not A or B.
Oh, and we want not B.
We
Yeah.
want not B.
only.
Well,
No, we don't
no,
want not B. We
we
want
want-
not a whole different. We want not ZQX.
How do you get that?
Not ZQX.
We're working on it.
Not ZQX.
So
I feel like it's gonna.
one second. This is gonna turn into. I don't know if this is the next step, but this will turn into ZPX at some point.
What will?
This, right?
That's not
Is
the
that
same
it?
thing.
Is that important at all?
No, not
Those
even.
aren't.
Oh, those aren't the same thing.
Those are very different.
But it'll be not ZPX, right?
You'll get not ZPX.
Right?
Uh,
I don't know if
but
that.
I don't know how you're gonna get any of those. Look,
Right
you
here.
got a bunch of things with Q in it.
Yeah.
And you know that you need to use the things you have with Q in it to get something with Q in it.
Yep.
So we're not going to be messing with any P's or I's.
Until the
We're
end.
just going to be doing Q's. And what do you need to get? You need to take some combined together, and you need to get a not what? Not ZQX, and you're done, right?
Yes.
Let's look.
Oh,
at
we might
these.
not have even needed this piece. Oh, maybe we did still. Okay, so here's what you need to get. The only way that we get new ones of these from these is we're implying something.
Wait a minute.
What has to be over here to give you this?
Wait a minute. Well, I already have that.
No, he's saying.
What in
he's
terms
saying-
of Q's needs to be over here to give you this?
He's saying that's A.
Not without that.
No, this right here. Y, Q, X, and Z, Q, Y.
Okay, so
No,
here's
or
what I'm thinking. Here's what I'm thinking.
And
We're gonna have this, and this is so we're gonna have XQZ or not XQZ, right? Obviously.
Sure.
Oh, that still doesn't get around.
look at this. This. What about this? Y, Q, X, and Z.
Which is
XQZ.
why?
That is equivalent, correct?
What do you? Oh well.
What I'm saying is,
Okay.
Hold on.
This
YQZ
this
and
is equivalent,
XQZ.
not YPX,
No,
not YQX,
this
not ZQX.
implies YQZ.
So these expressions.
This is the
But there's a
Well, I don't know what
sign.
you're trying to. Okay,
I'm
now you got nothing.
What? Here, Jake. It's this. Oops, I did that backwards. Right? Am I right? No, I'm not right.
Yeah, no.
Okay, I'm just gonna plug it in. I don't know what I'm doing. It's gonna be. I don't know how to deal with the knots. That's my problem.
Okay, maybe all the terms are throwing you off. Alright. So you want how do I say this roughly? You want, so if we write this in the terms
This
of
is equivalent to
Thank
X,
you.
Y,
Can we
Z.
do what Donnie's doing?
and B implies C is what we have right here.
Uh-huh.
And we need something logically equivalent with a not C right here. Okay.
Not
Here's what I know how to do. I know how to go, not C implies not A or B. But I don't know how we're gonna go that way.
That's not true.
So
That's the consequence.
let's just mess with it like this and see if this works. So this is the same thing as not this or this, right?
Right.
So this is the same thing as not A or B. Oops, not
A
A
and B, right?
or C, right?
And then you can distribute this.
And then we could factor out a not if you want. To switch this to.
And.
What?
Okay, okay.
No.
Well, hold on, maybe we
We
don't
could.
want that.
I mean, it's possible.
Let's see.
and B
Without changing this,
and not C.
what was I thinking? Because we need to get a not C here and have it logically equivalent. If I know that A and B implies C,
Should we look at our list of
do I know that
topologies?
not A
Let's just look at
and not B implies not C? Does that follow? Are those the same?
We asked that
We
question
just
a
had
while
that
ago.
and that.
No, you didn't have it like that. You were also trying to switch places around.
You have that and that.
No, that's still not what I have captured. That's not what I'm after. I'll just write down the implication. The implication is, take this, not Z, Q, Y, and not Y, Q, X implies not ZQX.
How did you get that? Using number one?
Mm-hmm.
Right, that's what I was trying to do with that. So
But notice that the Y's are both interior on that.
How did you get that from number one?
How do you do that?
he's just saying, look at the form.
He just nodded A and B, that's the inverse.
Yeah,
not-
these need to not be nodded.
No, those are not it.
Fine.
Not ZQY and not YQX gives not ZQY.
So you're saying here that not A
But that's not the same thing as that.
and not B implies not C.
Because this is not a knotted version of anything up here.
Yeah, it's not.
Well, actually, up there, no, it is. ZQY and YQZ, or YQX implies
Z,
ZQX. This is a knotted version of this. So we know that we can do this.
No, it's not.
Yeah, it is.
This has got to be or.
Oh, you're right.
That has to be an and.
So let's just mess with this. Let's do this. Let's pull out the not Z, Q, Y, or Y, Q, X, right?
Mm-hmm.
Implies not Z, Q, X. Now,
Okay,
let's interpret this as not this or this. So now we have Z, Q, Y, or
YQZ
Y,
or
Q,
not.
Z.
or
No,
not.
YQX.
YQX.
Yeah, it's because I'm looking on
Or
not ZQX.
not
No.
Z, Q,
Right.
X.
Right.
Now we know this is false, and we know this is false. You have them right here and here.
Mm-hmm.
So we know these two are false, one of these has to be true, therefore this is true. And that's how you get it.
Jake, you were going down that way.
I was
So-
going down that hole, but I was misplacing my
I
X.
mean, erase it and start from the beginning.
Wait. I gotta
Jake,
gotta
you
remember
said,
this
well,
first,
all
so
those
that I don't
could
get
be
lost in
true,
it.
but then we just didn't check with our facts.
I'm gonna start with
Which
this.
ones were false?
Gonna substitute. We're gonna get to this by using that number 2. I don't even need to do that part, do I? I just need to factor that out, the not out.
Yeah, you don't need 9 or 10.
Wait a minute.
You don't need 9 or 10. You can go from 8 to 11.
Well, you need to know that you can get X cubed.
So this is going to imply.
You don't
what
need
does
X
this imply?
What time is it?
It's like 8:45.
Yeah, we might need to just move on and come back to this next time.
We're
We
so
have-
close. We're so close.
Even if it's not making any sense to me.
Yeah, do it as homework, we'll come back and we'll just have written out versions ready to go.
Okay, I'll take a picture of the board. But I need to make
Because you don't have a video.
You know,
Yeah, you have the video on it. But,
just stand back a little bit.
so we'll do this problem.
I'll take a picture anyway.
I don't know what number it was,
Do not be gambled.
but I will just, what number was, I know that there was a number that I want to do with this. So we'll come and we'll just do this problem next time.
Cheers. That was frustrating. Got so close.
We did it.
Basically.
Well, we'll come back to it. And we'll make it all make sense. But, yeah, you guys go tackle that problem, see if you can do it.
You leave our meeting. You want my phone?
I need.
Are you gonna fulfill my 2 requirements?
I need some branches hauled off of the guys.
I'm sure Caleb and staff are committed to
Well,
their schedule.
what are they doing? I don't want to like completely.
What are they doing? +1.
Caleb was gonna do.
Alright, you guys can talk about work later.
Yeah.
Let's continue. Okay, so section 4.2. So section 4.2 is where we're once again going to introduce interpretation, talking about whether or not an argument is valid, and then talking about whether or not premises are consistent. Same exact conversation we've had before, but last time we only had sentential interpretation to work with. Now we're just going to use interpretation. We're going to come up with a definition of interpretation in this section. With me so far?
Yeah.
So one of the first things that the author is going to talk about when we start to do an interpretation of a sentence is we have to pick a non-empty domain of individuals to attach with the sentence. So pick one of his that he has real quick. So he has something along the lines of, for all x, h applying to x implies m applies to x. So I'm guessing he was using human and mortal, where x was the set of all people. That's one interpretation. So I pick the domain to be the set of all people, and then I can make h is human and m is mortal. I could also come up with an interpretation of this that uses numbers. So I could pick this to be all numbers, and I can make I could pick my domain to be all positive numbers or something like that. And I can make h equal to the predicate less than 4, and m equal to the predicate less than 7. So for all x, x being less than 4 implies x is less than 7.
Right.
That would be a true interpretation. A false interpretation would be, oops, switching these, keep that 4. No, now make this a 7, and this a 4. There's a false interpretation of the sentence, but still an interpretation of the sentence. So the first thing we need to do when we are doing the interpretation of a sentence is pick a non-empty domain that we're going to interpret the sentence with.
Which we've been doing before.
Step 1. We've been kind of assuming it behind the scenes. When we were talking about people, we knew it was people. We were doing it behind the scenes, but from here on out, we're going to have explicit domain that the sentence is talking about. Okay? So, picking numbers is called an arithmetic interpretation, which is a very common one. So for those ones that we were just working with, so we were just working with the two premises for all x, for all y, for all z. If x, q, y, and y, q, z, that implies x, q, z. And for all x, for all y, we had
XQY or YQX.
xqy or yqx. So an arithmetic interpretation that we could make for this q is less than or equals. So if I take every q and I replace it with less than or equals, you'll notice that this is now true for all numbers.
Right.
So that is a valid interpretation. So I can do less than or equals, 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 right? And there's a true interpretation. If I would have done just less than, notice that this would have been a false interpretation. Why? Because it's not true for all x, y that x is less than y or y is less than x.
Right.
What if x and y are equal?
Right, they have to be. Well, they don't have to.
Notice that this is always true, but if I just make it less than, that's not necessarily true. 3 is not less than 30. So if I make x and y both 3, then this wouldn't be true for just less than. But for less than or equal to, it works. With me?
Mm-hmm.
Jake?
I'm not with you for the reason of we're using for all x, and maybe I'm.
For any two numbers you pick, it is the case that the first is less than or equal to the second, or the second is less than or equal to the first.
Okay, I understand that one. But
Oh, for this one?
Yeah.
For any three numbers you pick, if the first is less than or equal to the second, and the second's less than or equal to the third, the first less than or equal to the third.
If we're going with unification, parentheses, yeah.
Yeah, oh, sorry, yeah. If this, then this. Good?
Yeah.
Okay. So... And then with the same example that we just did, you'll notice with our definitions, I can't remember exactly how they were, it was for all x, for all y,
X, I, Y.
x strongly preferred to y is logically equivalent to y is not less than or equal to x.
Makes sense.
And then, same thing for all x, for all y. If x is, we'll say x equal to y, or indifferent, is logically equivalent to x is less than or equal to y, and y is less than or equal to x.
Shouldn't it be y is greater than or equal to x on that top one?
Yeah.
If x, oh, did I switch it? If x is greater than y,
Then y is not greater than or equal to
then y, oh yeah, I meant to do it this way, right? Keep them all going the same way. No. If x is less than y, then y is not less than or equal to x. Same thing. Okay. So if we do this arithmetic interpretation, notice that this is how it changes our definitions.
So an arithmetic interpretation is basically a sentence or interpretation that uses numbers.
Yeah.
Okay.
His usage of that is if you're going to make. So when we do an interpretation, once we pick a domain, we also pick predicates that make sense on the domain. So I know the predicates I can use with numbers, like less than, equal to, less than or equal to, even, odd, prime. You know the predicates you can apply to number. So basically what we're going to get to is when you do an interpretation of a sentence, one of the things you have to do is pick a domain with that sentence. You're going to have to replace all the terms in the sentence with elements out of your domain. And you're also going to have to replace all the predicates in that sentence with predicates that apply to your domain, that are defined on your domain. In short, is where we're going to be on. Make sense? And we don't necessarily have to do it as a arithmetic interpretation. It's just a very convenient interpretation to do a lot of the times. Maybe thinking about the Q's and P's and all that is a nightmare in your head, and if you were to switch it into less than or equal to and greater than signs, then you can make more sense of it.
Yeah, it makes way more sense. Smart.
And you're still proving the exact same thing. Right? So, an example of an interpretation of a formula having free variables. So, let's see. Is that the first place where he talks about how to handle free variables? The two examples considered are not intended to foster the idea that interpretation should always be arithmetic. Consider
Right, that's
this.
why I started wondering.
We could do something that's not arithmetic. Okay, an example of an, so I think this is the first time he introduced how to do free variables. So far we were just talking about picking the domain and picking predicates that make sense with your domain when you're doing interpretation. And don't worry, we're going to get to a final definition. This is just building up intuition, getting comfortable with doing some, and then we're going to get the full definition. So the next thing he's going to say is, well, what about free variables when we want to do interpretation? So look at if we have a sentence like x is preferred to y implies for all, will someone just read that to me?
For all z, x, i, z implies.
X, I, z?
Well, I don't.
Is it
X,
different?
I, z
Implies z preferred y.
Which means an equal, right?
implies what?
Z
I can't remember the
preferred
exact definition.
p.
P, y. X is preferred to y, then for all object z, if x and z are indifferent, okay, yeah, that makes sense. So if you know that x is preferred to y, and x and z are indifferent with respect to each other, then z is also preferred to y,
Right.
right?
What did that mean, x equals z? Or that would be the...
Yeah, if we do this arithmetic interpretation, then
Oh, it's
x is
arithmetic.
equal to z,
Mhm.
is what this is saying. Yes. So a true arithmetic interpretation of that is easily found when we use, right. So he was specifically talking about, okay, what do we do with free variables? Because notice we can't call this true or false now. This, and this we knew how to deal with because there were no free variables. Notice now in this sentence we have a free variable. In fact, we have two free variables, right?
Mm-hmm.
So when you have free variables and you're trying to do an interpretation, you have to replace your free variables with constants in your domain.
You have, say that again?
When you're doing an interpretation and you have a free variable, a free occurrence of a variable, you have to replace it with constants in your domain.
What is the...
So a human being.
A particular element of your domain. Particular human being, or if we're going to do an arithmetic interpretation, a particular number.
Right.
Why do we do interpretations?
An interpretation enables us to go from a formula to a sentence. Something that's true or false. This is not true or false. Once we do an interpretation, then we're going to have something that's true or false. Well, not necessarily, but we use it's the use of interpretations to give you sentences, things that you can evaluate as true or false, because then we can get tautologies. What's a tautology? A tautology is ultimately going to be a formula that's true under every interpretation. In other words, it's always true.
This actually makes sense.
So we
why
define-
mathematics builds the way it does. Sorry, that was.
Yeah, so we define tautologies in terms of always being true in interpretations, and so we need to know what an interpretation is. Notice our formulas aren't always true, so we need to know how to make things that can be true out of them, sentences out of them, the way the author uses sentences in this class. So, if we want to make this into a statement that's either true or false, we've got to replace the x and y with actual numbers, but we can leave our z as is because it's a bound variable.
Right.
So you can't call this true or false, but I could do something like, if we're doing an arithmetic interpretation. So remember our p we were doing is less than, our z, our I as equals, wherever we have it, and our p as less than again, right? So we're saying, if 1 is less than 2, picking 1 for x, 2 for y, particular elements, and a predicate that makes sense in our domain. So the domain I'm using is numbers. I need to pick a number for x and a number for y.
We use intentional interpretations already.
We've used, right, so that's going back to what I was saying at the beginning. So far, the way that we've been identifying tautologies is, if it's true under every sentential interpretation, then it's a tautology,
Right.
right?
Right.
But it's possible that there's things that are tautologies that aren't true under every sentential interpretation.
Oh, that's what
So
you're rectangle.
yeah, so interpretation is a weaker restriction than sentential interpretation. It's like if I'm interested in rectangles, I can say, well, if it's a square, it's a rectangle. So here's our sentential interpretations. They only give us squares. Our squares are rectangles, so we're good, but we want to work with all rectangles and not just squares.
And
So
our
we want to work with
rectangles is small
tautologies that are always tautologies, not just tautologies under sentential interpretation, not just tautologies under sentential interpretation, we want tautologies under interpretation.
So are we going to get a whole new list of tautologies?
No, all our tautologies, those were tautologies based off of the sentential connectives, and those still work. We erase the steps, but one of the steps that we use is
Go to
sentential, using our sentential connectives, using those tautologies that you know and love.
Right.
And that's still the heart at a lot of these proofs as we go. Yeah. So our other rules are going to be basically, how do we substitute in predicates? How do we get rid of free variables? How can we add or get rid of quantifiers? But we need to go from sentences to sentences. We need to go from true sentences to true sentences. That's ultimately what we're trying to do. An axiom is a set of sentences that you can assume that they're true and determine what's true if they're true.
Right.
And that's what math is. It's always statements, sentences, things that are true or false. Make sense? Okay. So, we've got this. We're going to do an arithmetic interpretation where we're going to make the predicate p be a less than symbol. We're going to make the indifferent predicate be equals, and we're going to make this less than. And then pick two numbers, doesn't matter. Give me an x.
1,
1. Give me a y.
2.
2. So now we got this implies for all z, that one doesn't change. 1 equal to 2 implies
No, it's 1 equal to z.
1 equal to z, thank you. 1 equal to z implies z is less than 2. So for all numbers, if if it's equal to 1, then it's less than 2. Since 1's less than 2.
You have cleared up so much.
Okay? So this is a true interpretation. We could have also made false interpretations. Remember, interpretations are just enabling us to call it true or false. Right?
Yeah.
Okay. So this, we couldn't call it true or false. This, we definitely can.
Yeah,
Make sense?
because your x and your y can be any range of, can be any two numbers, right?
Well, down here, they're not even necessarily numbers. We don't know anything about them. It's
Yeah.
just x, p, y.
So we don't know if it's true or false.
Right. We can't say anything about this.
If we know that x
But we
is
can't say
3
anything
and
about
y
this.
is 2, then we know that that statement's false.
Yeah, if we would switch x to 3, and remember, if you switch it in one place, you have to switch it in another place.
Yep.
So 3, that makes this 3. But yeah, we overall have a false statement.
Okay.
Well, actually, we still have a true statement. because you have false implies.
If 3 is less than 2.
Yeah, false implies false, so it still happens to be true.
So it's a
But-
tautology basically.
That
makes
was,
so much sense. Yeah, if 3 happens to be less than 2, then yeah, anything can be true.
Okay. So, and we obtained the arithmetic truth, blah, blah, blah. Yeah, we went over that. Okay, to simplify the definition of interpretation, so I didn't even bother saying this, but remember our interpretations. Remember our terms, there were 3 types of terms. And I always just talk about it like there's 2 types of terms. I always just say variables and constants. The author says there's variables, there's names, and then there's descriptions. A name would be like Isaac Newton, a description would be the greatest mathematician of the past 3 centuries. Both of those are describing a particular person. One's a name, one is a description. The author just says, for the sake of keeping our definitions clear, we're not going to consider the description parts in our interpretation. You're just going to use names. But if you just think about variables and constants, we don't need to worry about that. So I just think about it in terms of variables and constants. So terms are variables, constants, and then the product of applying operators on terms, like plus. The author doesn't really go that much into an operator. I think he comes back and mentions that the operator has to be close. So far we were talking about terms and we didn't have a very precise definition. We said terms are things that either name or describe something, or they name and describe something when you replace all the variables with names or descriptions, right? So terms are either constants, or they result in constants when you replace the variables with constants, right? So here's a term, here's another term. 2 plus x is a term because when I replace my variable with a constant, when I replace that with a number, I still just get a constant. Make sense? So a term is something that's either a constant, or when you replace all the variables with constants, results in a constant, in other words. Okay?
So we can't. So all variables are terms basically as well.
All variables are terms by themselves, all constants are terms by themselves, but then we can apply operators between constants and variables to get terms still. So you can kind of construct terms by applying operators to them. Now, what is an operator? We're concerned with a specific type of operator here. We're concerned with operators that have the closure property. What that means is that the operator takes elements in your domain
Puts them in
and
the domain.
spits out elements that are also in your domain. So for example, if we're talking about the integers, 1 divided by 2 is not a closed operator on the integers. 1's an integer, 2's an integer, but when I do 1 divided by 2, what do I get?
1/2.
1/2, which is not an integer. So the author is going to basically make the point that if your domain is going to be something like integers, you cannot use an operator like divides.
Right, there you go.
It's not closed.
Because it's not closed. It can spit out something that's not in your domain. So your operators not only need to take elements in your domain, but they also need to spit out elements in your domain.
Does that apply outside of arithmetic? In like a human sentence?
In a human sentence, geez, what's an operator for humans?
I don't know. Maybe.
Yeah, we won't worry about it right now. Ultimately, we're working up to the foundations of mathematics, so we're interested in operators that apply to numbers. But yes, it could apply to humans somehow. If you came up with some operator that takes some humans and produces some humans, like some operator that takes 2 humans and ends up with a new human, some sort of fusion operator, yeah, that could be a thing, as long as the human spits out. But if I take 2 humans and I fuse them together and a frog comes out, and my domain was humans, that doesn't work. Anyways, he'll have more to say on operators here in a sec, but So let's look at another one. So this one's with cities. We're looking at the sentence. X is a city and X is larger than San Francisco. X is a city and X is larger than San Fran. Alright. So, looking at the sentence, we're going to do an interpretation of the sentence. First off, X here is,
A constant.
well, let's think about what this is, what exactly this sentence is saying. Let's try to codify this city. Or let's try to codify the sentence. Well, first off, we know that San Francisco is just a constant, right? So we can just let A for San Francisco, right?
City is also a constant. Well, X
No,
is also
city is a predicate.
X
Is a city is a predicate. And is larger than is a predicate.
Yeah, we can do that. But the point that the author is going to make is, in the sentence, we have X as a free variable, and then San Francisco as a constant.
But X isn't a free variable.
It is. If I go through and I replace X with an actual city, that's a concrete city, this is now either a true or false sentence.
But if we were to codify that, we would say for all X, wouldn't we?
For every city, if X is larger than San Francisco,
No, for
you could say that, but that's not what this is saying.
Right.
For everything that is.
This isn't saying that there exists a city that is larger than San Francisco. This isn't saying that for all cities, X is larger than San Francisco. This is just saying we have this free variable X that's a city and X is larger than San Francisco.
Right.
So one thing we could do is we could replace that X with the city. We could also do an arithmetic interpretation, right? We could do.
What are we trying to do in general here? I'm missing the common thread in all of these examples. Like, what are we doing?
We're getting used to doing just interpretations of sentences and different types of interpretations of sentences. So we're learning the different rules for when we do an interpretation of a sentence. So we knew that once we pick a domain of things, we have to replace. We need to replace our constants and free variables with elements in our domain. If our domain is all cities, then we can only replace X with cities. If I decide I want to do some other interpretation on this, I'm going to need to replace X and this X with things that
I see larger than San Francisco.
are elements of our domain. I'm going to need to replace San Francisco with elements of our domain. And I'm going to need to make sure that the predicate larger than makes sense in our domain, and the predicate is a city makes sense in our domain.
Right.
So another way I could do
Change the
this
predicate.
is I could do something like 2 is a positive number. And 2 is greater than 3. So what did I do right there?
Is less than.
I replaced 2 with an element of my domain, positive numbers. I replace is a city predicate with is a positive number predicate.
Okay.
I replace is larger than with is greater than.
Then you want me
And
to
I replace San Francisco with 3. This happens to be a false interpretation, but it's still an interpretation. I replace all my free variables, X, with elements of my domain. I replace all my constants, San Francisco, with elements of my domain. And I make sure that my predicates, larger than, and a city, a positive number, made sense as predicates in my new domain.
Right.
Why is it false?
Just two.
Because 2 is not greater than 3.
Oh, your statement's false.
Yeah, so it's a false interpretation, but it is an interpretation.
It's
Okay.
an interpretation.
I replace my free variables with elements in my domain. I replace my predicates with predicates that make sense for elements in my domain. And I replace my constants with elements in my domain. Right? Now this could have been, instead of something like this, it could have been, there exists X, where X is a city and X is larger than San Francisco, right? So now, in this case, X is no longer a free variable. So when I'm doing an interpretation of this now, I don't just pick some number and plug it in for X. So let's do another arithmetic interpretation of this. What are we saying?
There
We're
exists
saying
number X.
there exists X such that X is and it doesn't matter, we can say a positive number, whatever domain we want. In this case, we're doing positive numbers. And x is greater than, and then pick whatever we want for San Francisco, because that's still just constant. So here's another interpretation where we put this quantifier here. So since we put this quantifier, x is no longer a free variable. So now we do not change it in our interpretations. We only change the free variables in our interpretations. Just like we did over here. When we went from our q's, our i's, and our p's to our less than or equals, and greater than's, or less than's, we didn't change any of our variables that we were talking about because they were all bounded. Does this make
This
sense?
one wasn't
Yeah.
bounded though.
It wasn't at first, so we did it that way, and then I put this on, so now it is bounded, and I'm doing it again. So it's like two examples in one.
Okay.
I shouldn't want to rewrite it. So you go with me, we did two examples with the same sentence. We did an interpretation of just that, and now this interpretation with the existential quantifier on there.
So can you tell us the difference between a sentential interpretation and just an interpretation?
Are
Like
we
the
gonna
actual
get to
difference
that
of
right now?
definition?
And in this section.
Yeah, we'll get to the exact definition of an interpretation. But a sentential interpretation, the only structure it preserves was your sentential connectives. That's the only structure it preserved. Notice how much structure we preserve in interpretation here now. We kept these quantifiers, we kept the variables that were bound,
The predicate.
we kept the predicates, and we kept the sentential connective.
So a sentential interpretation is not an interpretation.
It is an interpretation, it's just using, it's just.
That is correct.
Okay?
What? A sentential interpretation is an interpretation.
Rectangle's not a square, man.
A sentential
Yeah, but a square is a
interpretation
rectangle.
Right. So,
is not an interpretation. That's not what we were saying with squares and rectangles. We were saying if something is a tautology under every sentential interpretation, in other words, if just its being an implication makes it a tautology, then all this structure that we added, it's still going to be a tautology because just the sentential connective made it a tautology. That's what we did before.
But if you
The
have all
only
that,
structure we were looking at was sentential connectives. If just the sentential connectives alone made a tautology, then it's going to be a tautology. Because notice every interpretation also keeps this.
sentential connection.
So every interpretation is a sentential interpretation. Not every sentential interpretation is an interpretation.
that verbiage is pretty weird, but it makes sense.
Did I lose you in that? From a sentential interpretation perspective, this statement is just A implies B.
Not very fast.
It's just an implication. Right? So we took it before it had the Q's and whatevers, and we took it from the Q's to this. So we went from A implies B to C implies D, so it was just a sentential interpretation. But it was more than just a sentential interpretation, it was an interpretation. Make sense? So every sentential interpretation is an interpretation. Oh, I said that backwards.
Is it the back-
Every interpretation is a sentential interpretation.
Yeah, it's
The interpretation we did here was still a sentential interpretation. Going from this to this is still a sentential interpretation. It still maintains its logical structure.
That makes sense.
We good on that?
yeah, it's just usually like grammatically a sentential interpretation would imply that it's an interpretation.
Basically, the author made in chapter 2, all we're going to worry about is, do the sentential connectives by themselves give us a tautology? And now we're looking at, okay, let's look at the entire structure of the sentence. Because if the sentential connectives alone make a tautology, we're already done. And we use those tautologies all the time internally as we're doing our proofs. Right? Am I just losing you more?
No. It makes total sense what you're saying. Especially when you simplify it to A and B. All that statement up there is A implies B.
Yeah, we took this from a A implies B to a C implies D. It was still just an implication when it was all said and done.
Right.
Yeah.
Still some tension
So it was still its intentional interpretation. We still preserved the, I can't remember the verbiage we had for it, but something like this intentional form or something like that of it. The logical form, the logical structure. I don't know what we call it. But we had a word for it that we were preserving. So all our interpretations are still going to preserve that. It's just they're going to preserve more than that. They're going to preserve more information. We care more about than just the fact that this was an implication. This has a lot more information than just A implies B encoded in it. And we want to preserve as much of that universal information as we can. Maybe that's not technically true. We want to preserve enough to develop math. Okay. What time is it?
2.
Because we still have a ways to go on this. And this honestly is going to be the most confusing section, so I really don't want to rush it. And now we got through 2.1. Next time we come, I can have all our major definitions already written out, and we'll be able to go through a lot quicker. So I'll restart this section next time. So next time we'll restart with 4.2. We'll restart going through all of it. That way I can get all the actual definitions written out. Because I actually want to start with, go over the definition of interpretation, and then go back and go through the examples. I think that's better. I don't
Yeah,
like
I
how he
like that a
keeps
lot
doing
better.
this. I hate digging for a definition. It's like, give it to us, and then we'll see how it's used. It drives me nuts.
My brain makes so many leaps. I just put it like a gospel.
Alright, so we'll do that next time. I don't want to keep pushing this because I don't have it organized, laid out to give it to you guys. One thing I do want to show you guys, because you are going to go through and read this, right? This is dense stuff. You're not going to get this once just listening to me. You need to go, try reading it, struggle with it. You're going to say, wait, that didn't quite make sense, go back to it. And maybe some of the preliminary stuff I've already given you will help you make sense of it. Like, one of the first things I missed going through it was the flagged variable bit.
Right.
Oh, but that was in the previous section. So, I guess that doesn't count for this. Anyways, yeah, at least go through 4.2 because this is really dense and this is getting at the heart of all the theory that we're using from here on out. It's basically just these interpretations. So, make sure that makes sense. One thing I want to show you guys before we went is he has a brief discussion here where he goes on a little bit of a tangent to some stuff that you guys might not be familiar with, and he's trying to give you some perspective of where this kind of stuff is used. So, two famous theorems that that he's going to bring up as a conversation here is called, one is called the halting problem, and one is called the completeness theorem. So, one of the things we're going to be interested in, once we have all our interpretation figured out, what we're going to be interested in is if I have some given set of premises, and I have some conclusion that I'm trying to prove. Once we introduce our quantifiers, our predicates, our terms, everything, remember that showing that our axioms or our premises imply this means that this logically follows from these, right? Which means that under every interpretation, these logically imply this.
Right.
Is what, or tautologically imply this, is what we're ultimately going to be getting to, right? Did I lose you in that verbiage already?
No, it's just like it.
Just so it's
G.
Okay, so then one of the natural questions that came up early in the 20th century was, is there some systematic way to do this? Is there some systematic way to say, if we have these premises and you're trying to get this conclusion, is there some systematic way, some like big massive truth table way that we can just plug it in, let a machine run and say, yes, this does follow from this? Is there some rule, some formula, some systematic way that we can show that this does or does not fall from these always and forever? Do you understand what I'm trying to say?
Yeah.
Like with the truth table, there was a systematic way when we didn't have all these. When we only had the sentential connectives, all you have to do is make a big old truth table, and if your last column just had truths, then it was tautologically implied, right? So with all this other stuff that we're adding, is there still a way to get from this to this? And the answer is no. And this is called the halting problem. Now, the reason it's called the halting problem has to do with how it's using computer science. So I'll try to make it appeal to your intuition, and then I'm going to have you watch a little proof of the halting problem, because it's actually real easy to understand. It's actually logically impossible to have a systematic way, a machine, basically a computer, that can always determine that this logically follows from this. To always determine. We're not saying computers can't do some proofs. We're saying you can't design a computer that if you go find some conclusion that you're trying to prove, you can't always just throw it in there and say, hey computer, can you prove this from these premises? Is that possible? Yes or no? And have the computer always answer the question. That's an impossible computer to build. Okay? Do you understand at least what I'm saying so far?
Yeah.
Okay. And the way that they're going to frame this is called the halting problem. The halting problem, the way it's told to computer scientists is, there's no way to know in advance, there's no systematic way to determine in advance if your program's going to crash. The only way to know that your program is going to crash is run it and see if it crashes or not.
And then you have to go find the wire.
Similar thing with getting this in. There is no way to systematically know if I'm running a computer and whether or not it's going to find this thing, because it could just be taking a really long time. Because all I can really do is keep trying things, keep trying things, keep trying things. So maybe your computer goes on forever, maybe it got stuck in some infinite loop, maybe. The point is, since it potentially takes an infinite number of time to find something, or maybe it's impossible so it takes an infinite number of time, there's no way to distinguish those two. So you can't say, well, if you let it try for 1,000 years and it didn't find it yet, then that means it's not possible. No, it doesn't. Maybe it's a proof that took 1,000 years and 1 second to do because of how many operations it had to apply. So you never know how many steps have to be applied to get there. There's no rule. You see what I'm saying?
Yeah.
So the way that's done in computer science is, there's no rule that says when your program's going to crash. The only way to know if it's going to crash is run it and see if it crashes. And so that's why it's called the halting problem, because your computer crashes, it stops going. It hits some infinite loop potentially. You feel like you have intuition for what I'm saying?
Yeah.
And how the halting problem is related to this thing? Because they're logically equivalent. So now I have you watch a little proof of the halting problem, because it's remarkably straightforward. And it's a nice little animated thing to show it. Is that too fast? Alright, proofs that computers can't do everything. A few things computers do really well. Really dragged out.
This is computing machine A. A solves problems in arithmetic. It receives a problem written on paper, and it prints the answer.
Speed up just a little.
It always prints the right answer. Here's another computing machine, C. C plays checkers. It receives the current state of the board, and it prints how it would move one of the red pieces.
AlphaGo.
C plays checkers so well, it will never lose a game. A and C are machines we can already build today, and computers keep getting smarter and smarter, so will they eventually be able to do everything? Let's feed A with a board of checkers. A was not designed to handle this kind of input, and when it tries to process it, it gets stuck. The same thing happens to C when fed with a question in arithmetic. Let's draw a blueprint of A. blueprint is detailed down to the level of the logic circuits, and it fully defines how A works. We are now finally ready to introduce a marvelous machine called H. H solves what is known as the halting problem. It can analyze the blueprint of another machine and determine which inputs are good for it and which will cause it to get stuck. It receives the blueprint of the machine to be tested and an input to test it with. Based on the blueprint, H simulates the given machine on the given input, and then determines if it gets stuck or not. H solves the halting problem perfectly. It always prints the right answer. Here are two more examples with the blueprint of the checkers machine. H is a nice machine, but can we really build it? We'll now prove that its very existence is logically impossible.
Would that mean that because it has to run it each time?
Let's assume that H does exist.
Well, you just have a contradiction.
We'll place it on this stand for reasons that will be made clear in a minute. Recall that we assume H solves the halting problem perfectly. It should always print the correct answer. We are about to put this to the test. This is a photocopying machine. It simply prints 2 copies of its input. We'll place it behind H.
So then you just need to slide them down.
Here's another simple machine. We call this one the negator. When the negator receives the words not stuck, it gets stuck. And when it receives the words stuck, it does not get stuck. And it prints a smile. We'll place it in front of H. Let's wrap it all in a neat package we call the X machine. X has 1 input and 1 output. Let's draw its blueprint. As before, this blueprint fully defines X. What do you think will happen if we feed X with its own blueprint? Will it get stuck? Let's find out. P simply duplicates our input. H receives 2 copies of the blueprint of X. It should now determine what happens when X is fed with its own blueprint. Let's assume it says, not stuck. N negates that and gets stuck. So feeding X with its own blueprint causes it to get stuck. But H said it wouldn't. H was wrong. Let's try again. This time, we'll assume H says, stuck. X didn't get stuck. But H said it would. H was wrong again. But H is supposed to always be right. This is a contradiction, proving H cannot exist.
It is literally that simple. So this is a common proof that you do in a field called computation theory all the time. You show that if, well, they're kind of doing it backwards than how you normally do it. If you can solve the halting problem, right, then you build a machine that it doesn't work on. You build a contradiction.
Yeah.
Right? So the halting problem machine can't exist. That's the assumption we made. We said assume H exists. That leads to contradiction.
Right.
It's a reductio ad absurdum proof, right? Assume H exists and always gets it right. That leads to it always getting wrong. Therefore, H can't exist.
Right.
And then in computer science, what you do over and over, not computer science, computation theory, it's actually a field of mathematics, is you do a lot of proofs proving that what you're interested in is, can certain types of problems be solved by computers? And what you show is, if this problem were solvable by a computer, then I could solve the halting problem, which we know is impossible.
Right.
Therefore, this can't exist. So that is, so the author's going to have some discussion about this. He calls it the Alonzo Church I think that's his first name, Alonzo. His last name's Church. Church thesis, something to that extent. It's the halting problem, essentially. It's the idea that you can't take some set of premises and have a machine that can systematically determine that this will always, what can't instantly determine whether or not something logically follows from these. Right? Just like you couldn't always determine, does a machine getting stuck logically follow from whatever the blueprints are? Make sense? So the other one that he's going to talk about is the incompleteness theorem done by Gödel. I don't know how to pronounce his name. It's got one of the O's with the two dots above it. And what he proved is that there is no complete set of axioms to capture all. You could just pick arithmetic for our sake. You could have also said we'll just stick with arithmetic number theory essentially for now. There's no set of axioms that you could find such that you could determine every true number theory theorem from those set of axioms.
How did he prove that?
Yeah. That's very interesting how he proved that. And that's not as simple as this, so I couldn't just give it to you in 10
Guessing it would
seconds.
still be proved by contradiction though.
It has to do with an encoding, a prime number encoding, but how he did it, the author will have some brief discussions about how he did it isn't as obviously intuitive, but the author's going to have some conversation about. The first one was, can we always determine whether or not an argument is valid? Here's your premises, here's your conclusion. The second one is, do we have a complete set of axioms? Are the axioms that we have complete in that we can prove everything we want for number theory from that set of axioms? And the answer is no.
Doesn't that mean that there has to be an infinite set of axioms?
If you want them to be consistent. So what he showed is you either are going to have to have an infinite set of axioms. You can add axioms ad infinitum and still have them all be consistent with each other. Or if you were to add an axiom that then enabled you to prove everything, you would have also enabled a proof of a contradiction.
So basically you have to have a set of different axioms.
I don't know about have to. You can add axioms ad infinitum. If you're going to have, if you want to get as many results, if you want as many results as possible to be able to be proven from it, even then it's like we're comparing infinities, which is a weird thing to say.
Because it's like...
But yes, you can...
If you wanted to discover all true things, you'd have to have an infinite set of axioms. That
It's
doesn't
weird
make
when we're
sense.
saying it with infinities, but kind of, yeah. I think your intuition's
I
right.
realize what this proof is doing. I realize why they duplicate the blueprints.
Yeah.
You're
'Cause that
running the
is the
machine
machine. Right.
on its problem. You need
Right.
the blueprints of the machine and the problem it's solving. And the halting problem takes blueprints, takes the problem, and checks,
If it's
will it halt?
right.
And if it says it won't halt, it halts. And if it says it will halt, it doesn't. Right? Usually one of the
Why would you throw
paradoxes,
that not in there, not in the bottom?
that's what ties it all together.
So it makes it wrong every time.
Anytime the internal machine says yes, the outer machine says no. Anytime the internal machine says no, the outer machine says yes.
Well, you
So it's
throw not in.
designed so that the machine always contradicts itself. That's by design. It's kind of like a statement I wrote up there. This statement is false.
I know, I'm saying.
If the statement's true, then it's false. If the statement's
Can't
false,
you do
it's
that
true.
for all proofs? Just throw that little knot in the end and wrap it up and.
Well, remember what the halting problem did. It determined will a machine halt on its own on a particular input. So you ran the halting machine on itself, basically,
Right.
with a little bit of packaging to make sure that the outer machine always does the inverse of what the inner machine does.
Right, so we did a proof by contradiction.
Yeah, it was a reductio ad
We
absurdum.
found the computer.
Assume it's possible. Assume the halting machine. Assume that there's a machine that solves the halting problem. And we let it not solving the halting problem.
Right.
Therefore,
Oh.
the machine can't exist.
Perfect. Yeah, there you go.
Yeah.
That doesn't-
Yeah, it's a pretty simple little demonstration. Makes perfect sense. Little kitty video.
Okay. We go prove it
So yeah, well,
I'm kidding. I'm kidding.
dude, there's your proof already. Kind of. The point was he's gonna have conversations about these two ideas, and I just wanted to let you guys understand what the ideas were before we went back to it. So that's all I got for you for today. We'll call it good there. And next time we'll restart on 4.2. And as far as when school starts,